This is Applied Calculus, section 2.3, titled Continuity. We begin our discussion of continuity with an informal definition, which states that a function is continuous if you can draw its graph without lifting your pencil from the paper. So this graph on the left-hand side, you can notice that I can trace the graph in one continuous swoop. That is an example of a continuous graph. I didn't have to lift my pen from the screen. This graph on the right-hand side, from left to right, I can draw, then I have to stop, lift up my pen, draw, stop, lift up my pen, draw, and so on. So I have a bunch of discontinuities here on this graph because I cannot draw the entire function without lifting my pen at least once, and in this case, repeatedly. The formal definition states that a function is continuous at a point x equal to c if the following three conditions are true. The first condition states that the limit exists as x approaches c. Remember that condition 1, when we say the limit exists, this means that the left-hand side limit is equal to the right-hand side limit. Condition number 2 states that f of c exists. This means that there is a point at the coordinates c, comma, f of c, where f of c is the y-coordinate and c is the x-coordinate. That means there's no hole, there's no vertical asymptote at that location. And number 3 says that the limit at c is in agreement with the point at c. So we have a continuous curve at that location. Let's use the definition of continuity to identify all the locations where the graph of f of x is discontinuous, and we want to identify which condition fails. So we see right here we have our first discontinuity, and the reason it fails is that the limit from the left is not equal to the limit from the right. So we're going to say discontinuous at x equal to -4 fails condition number 1. Our next discontinuity occurs at x equals -3. And we see the left limit equals the right limit, but there is no point f of c. So condition number 2 fails. Our next discontinuity occurs at 1. And it fails by condition number 1. Meaning that the left limit does not agree with the right limit. And our next discontinuity occurs at x equals 3. And we see that it passes the first condition. The left limit and the right limit are in agreement. We see it passes the second condition. There is a point defined for x equal to 3. But in this case, it fails the third condition because the limit value at 3 is not in agreement with the point at x equals 3. So we can continue to use the definition of continuity to identify whether a function is continuous or not on its domain using algebraic methods. So we're not going to look at graphs. Instead, we see that for example A, that f of x is x plus 2. X plus 2 is a linear function. And we understand that linear functions do not have any vertical asymptotes and do not have any holes. So we expect all three conditions to be satisfied and for the graph to be continuous at x equals 2. If we look at example B, we see it as a rational function, and we understand that rational functions could have holes or rational functions could have vertical asymptotes. So if we factor the numerator x plus 2, x minus 2 over x minus 2, we see that the x minus 2's will cancel. And whenever that happens, that means that there is a hole caused by that factor. And we're going to have a limit that agrees, but we're going to have no point that exists at x equals 2 because of a hole, and that is the x value that they're asking us to investigate. So example B is discontinuous at x equals 2, and it fails condition number 2 because 2 comma f of 2 is not defined. Or you can say it does not exist. Example 3, that's an absolute value graph. We understand that absolute value graphs in rational functions will create a graph that disagrees at a point, and that this graph in particular is going to have a jump discontinuity. That's what we call this space between the two branches of the graph, a jump discontinuity. And that's going to occur at 0 because inside the absolute value and inside the denominator, there is no value being added or subtracted to x, so it's centered at 0. However, at x equals 1, we should be fine. If we put that point there, we see that the limit from the left and from the right will be equal, and that the point is defined, and that everything here is in agreement, the limits and the point itself. So example C, discontinuous at x equals 0, fails condition number 1. But it is continuous at x equal to 1, satisfies all three of the conditions. And if you have trouble seeing this, you can go to the graph. We can plug in the function, go to y equals on your calculator. Your numerator is going to be the absolute value of x, so we hit the math key, and then we hit the right arrow to get to the num menu. The first option is absolute value, so I'll choose that. I'll put x inside of it. I'll use my cursor to get outside of the absolute value bracket, hit the division sign for my fraction bar, put x in the denominator and hit enter. And when I hit graph, I will see that there is a jump here. I'm going to use the zoom button to zoom in. And I'm going to use the zoom button to zoom in a second time, just to show that that discontinuity is occurring around x equals 0, but that at x equals 1, we have a continuous graph. One-sided continuity is when we're looking at a graph inside of an interval, and we can see that, for example, we have a function that describes a semicircle, and it's got closed points on both ends. And we would only then evaluate the continuity from the left side moving in to the right, or from the right side moving in to the left on the interval. And we would say it would be continuous for that whole interval from -1 to 1 in this case. And we can read the comments up above. It says a function is continuous on a closed interval AB if it is continuous on the open interval AB and is continuous on both the right at A. So remember, A is the left part of the interval, so this would be our A. It is continuous moving to the right. And on the left at B, so the right-hand side is our B. That's the right-hand side of this interval. And we'd be moving to the left from here. So we can use the closed brackets. And then they give us a second example where we have a closed value at 0 on this square root function. And because that is on the left side of the interval, I can put a closed bracket because I only have to evaluate to the right side from the left bound. My right bound, however, has infinity in it, and you can never have a closed bracket with infinity. This next slide is introducing properties of continuity. If two functions are continuous on the same interval, then their sum, difference, product, and quotient are also continuous on the same interval, except for values of x that make a denominator 0. So this becomes helpful with rational functions and polynomial functions and any combination of functions, logarithms, and exponentials. And for example, if I have f of x equal to e to the x, and if I have g of x equal to log of x, we would say that this domain is x belonging to all real numbers, and we would say that this domain is x greater than 0. Therefore, f of x plus g of x would be the intersection of all real numbers intersecting, that's what this upside down u is, with x greater than 0. So how do we look at that intersection? Well, this is all real numbers from negative infinity to infinity. And then this is x values greater than 0. So everything that they have in common together would be applicable to their combination. So this new function would have a domain of x greater than 0. So here are some continuity properties of specific functions. If we have a constant function, remember that's a horizontal line, it is continuous for all real numbers x. If we have a function x to the nth power, where n is a positive integer, these are the terms of a polynomial function, x squared, x cubed, x to the first, again, positive integer, and we can go all the way up to 5th, 6th, 7th, any power. And since that's all the polynomial terms, well, they all have domains of all real numbers. So if we took a combination of x cubed plus x squared plus x, as we just saw on the previous slide, we can take the combination of their domains, and since each polynomial term is all real numbers, the combination would be a domain of all real numbers. So C and B are related. B would be the independent terms of the polynomial. C would be the combination And therefore, using the fact that we discussed on the previous slide, since each individual term has a domain of all real numbers, so does the polynomial that results from their combination. D is a rational function is continuous for all x except those that make the denominator 0. Remember, rational functions are a combination of polynomials in the numerator and denominator. So all real numbers except those that make the denominator 0, because that would then be undefined. And E, for n, any odd positive integer greater than 1, then the function f of x under that radical is continuous wherever f of x is continuous. And F, for any even positive number, it's continuous for any non-negative value under the radical. So we've emphasized this in the past. Cubed roots, fifth roots, seventh roots are all real numbers. Second root, fourth root, sixth root are only positive real numbers, or 0. Second roots, fourth roots, sixth roots have to have a non-negative result, because I cannot take the square root or any even root of a negative number. I could take an even root of 0 or positive numbers. So here's some practice using continuity properties without their graphs, just applying the general properties we saw. And here we see this is a polynomial, so it's continuous for all real numbers. For B, we have a rational function, and we see that this first parenthesis will be 0 when x is negative 2, and this second parenthesis will be 0 when x is 3. So for B, discontinuous at x equals negative 2 and x equals 3. Part C, we have an odd degree root. Odd degree roots are continuous for all real numbers. And part D, when there's no number there, it's understood to be 2 for square root. And we now have to take everything that's inside of here and say x minus 2 is greater than or equal to 0. And then we solve and get x is greater than or equal to 2. We just solve it like we would any equation. You add 2 to both sides. And that would be our domain for part D. Continuous for x greater than or equal to 2. So here are some problems from the exercise section of the textbook. It says sketch a possible graph of a function that satisfies the given conditions at x equals 1 and discuss the continuity of f at x equals 1. So something like number 9 says that f of 1 is equal to 2. So we'll draw a graph. 1 on the x-axis, 2 on the y-axis. F of 1 equals 2 means that there's a point there. And it says the limit of f of x as x approaches 1 is equal to 2. So we can draw any graph we want. And we see that the limit from the left and from the right are approaching 2. So it satisfies the limit part. And we see we have a closed point at 2. And that would be a sample graph for number 9. Let's look at number 11. Once again, we're going to draw our x and y axis. We're going to place a point at 1, 2. But this time the limit as it approaches 1 is equal to -2. Because I have a point at 1, 2, this must be an open point because we defined it as a function. And remember, functions have to be able to pass the vertical line test. So I can't have 2 points on that vertical line. I had to make the second one an open hole. But now I can make the limit approach -2 from the left and the right. So this is a sample of a graph that would satisfy problem 11. And again, you can draw this many different ways as long as we have an open hole with a graph approaching it from both sides, so the limit exists there, but then a point that is disconnected from that hole and exists at y equals 2. This type of a discontinuity is referred to as a point discontinuity, or many books call it a removable discontinuity. So that's the end of this lesson. Review the video, take notes, practice the problems, and bring questions to class.